Bonding part 2. Grab your notes and reference tables, we can check out some reactions. According to table I on page 5 of your reference tables, how much energy is released by each of these reactions below? Let's take a look at table I and see what we can find. I'm going to look for this reaction right here. 2 moles of carbon monoxide, CO, plus 1 mole of O2, oxygen, will combine and create 2 moles of carbon dioxide, CO2. I'll also look for this reaction over here. 4 moles of Al added to 3 moles of oxygen produces 2 moles of Al2O3. Now, when you're looking at these things, just be careful. There's a lot of different reactions that look kind of similar, and it's easy to get confused and pick the wrong one. But this first reaction on the left here is the one that's the 7th down on the list on table I, right under all the ones with CHs and CHO molecules and things like that. And it tells us that the energy change listed on here, it's labeled as a delta H, like this, is negative 566 kilojoules is the unit. That's the unit of energy. So this means that 566 is the amount of energy released, and the negative sign here is because that amount of energy is being given off. So remember earlier in the year we saw this, when it's a negative energy change, like an exothermic reaction, that's just because you're losing, releasing, giving off that much energy. So this is going to release 566 kilojoules of energy every time these molecules, the CO, the 2 COs, and the oxygen combine and make 2 molecules of CO2. On the other side, this other reaction here, it's going to be 2 lines underneath the previous example on the table I. This one tells us that negative 3351, so negative 3,351 kilojoules of energy are released every time you get 4 moles of aluminum and 3 moles of oxygen combining to make 2 moles of Al2O3. Now, on the bottom, the questions say, which of these 2 reactions releases the most energy when bonds are formed? If we simply look at these numbers, we can see that the second reaction releases a lot more energy, 3351 compared to 566. So if you remember from the previous lesson that the energy released when a bond forms gets given off when the things come together is the exact same amount of energy that would need to be absorbed to break the bond apart again. The same amount of energy you gave off over here to form the molecule and form the bond is the exact same amount of energy you need to add back in to break that bond apart and split the molecule up. If we look at this that way, then that means because this second molecule over here, this second reaction, has a lot more energy being given off, you need to add that same much more energy in to break it apart again. Because it takes that much more, it's that much tougher to break apart, that bond in the second example here that makes this second molecule is going to be much more stable than the bonds holding together this molecule over here. The harder it is to break apart, the more stable it is. So this guy over here, Al2O3, is that much more difficult to break apart, it's that much more stable than CO2. That being said, now we can finally get on to the main part here, which is drawing some electrons. What do we think about this first question here? What part of an atom helps it bond? What part of an atom is positioned near other atoms that a bond might even form? Think of the parts of the atom. The nuclei, the middle of the atom, is kind of buried down below. It's not exposed to the outside, so it really can't bond with anybody else. But the electrons surrounding it are out in the open. If you remember from our atomic chemistry chapter, the arrangement of electrons in an atom, especially the outer ones, is what's going to determine how that atom behaves. And things in the same column, the same group, the same family, they will all behave very similarly because they all have the same number of outer ring electrons. So we can show a visualization of this by drawing what's called a Lewis structure. You may also see or hear it called a Lewis diagram, an electron diagram, an electron dot diagram, a Lewis dot diagram, or any combination of those words. Why do we call it an electron dot diagram though? Well, gee, I wonder. Maybe it's because it's a diagram that shows electrons as dots. That would probably make some sense, right? As it says here, each diagram is an elemental symbol surrounded by some number of dots. In each diagram, the chemical symbol represents the nucleus of an atom of whatever the element is, as well as any electrons that aren't in the outer ring. So the inner electrons, or what's called the kernel electrons, if you remember that from earlier in the year. So basically that symbol just means there's some atom here, this is what the element is, and we don't really care about what's in the middle. We don't care how many protons and neutrons are in the middle. We don't care about the inner electrons. All we care about are how many electrons are in that outer ring exposed to the outside that might actually interact with some other atom. Now the dots drawn around the symbol represent just that, the outer ring or valence electrons, of which there can be anywhere between 1 and 8. So I think of it as if there was a box drawn around the symbol, and you can draw 2 dots on each side of that box. You can't draw them anywhere you want on the page, only on the direct top bottom, left, and right. So 2 on each side for a maximum of 8. So you might have 2 on the top here, 2 on the right, 2 on the bottom, 2 on the left, anywhere around that box, but only up to 8. You might have less than 8. A lot of times you will have less than 8. But that's the maximum you can have at any given time for any given atom. Let's draw some of these things. Our first step says write the element's symbol. Well, we know it's carbon here, so we can just draw a C, write a C. Step 2, count the valence electrons in atom of the element. Hopefully remember that valence electrons are the ones in the outermost energy level, which means that it's this last number in the line. So carbon has 4 outer ring valence electrons. So we now have to draw 4 electrons somewhere around this C, as we saw in the last slide there. Steps 3 to 5 say that I can draw up to the first 2 electrons on top of the symbol. So if I only have 1 electron, I'll only draw 1 electron, but if I have 2 or more, the first 2 will always go on top. Then any additional electrons beyond the first 2, I'll draw around the symbol going clockwise. So I'll start on the right, then go to the bottom, go to the left, and then start over because I'm going to spread them out so that I put 1 electron on each side before I give any side a second one. So I don't double up any side except the top where I start. I put 1 on each side, and then I can go back and do it. So I'm going to put my first 2 electrons up top, and then that's only 2. I have 2 more to do. That's electron number 1 and electron number 2. I still have 2 more electrons to go. So because it says I'm going to go clockwise, I'm going to head over to the right side of the symbol to do electron number 3. And then I don't do electron number 4 on that same side. I'm going to keep moving clockwise and put number 4 down on the bottom. Those are my 4 electrons, and I'm done with that one. Start first 2 on the top if you have to, and then move clockwise around. If I had a 5th electron, I would do it over on this side, and a 6th electron would go over here. Number 7 will go back down here, and number 8 will go over on the left again. But I don't. I only have 4, so I'm going to get rid of those guys and leave exactly what I had before. 1 and 2 on top, 3 on the right, 4 on the bottom. Let's try the other one. Bromine. It tells us bromine is Br, so I'm going to write Br on my page. Next, we want to count our electrons. It tells me that the last number in line here is a 7, so bromine has 7 valence electrons. We need to put 7 valence electrons somewhere around this guy. So on step 3, it says we can draw up to 2 on the top. I'm going to add my 2 up top. Those are my 1 and 2 electrons. I still have 5 more need to go. So I'm going to put my number 3 on the right, moving clockwise. I will put number 4 down the bottom, just like I did with carbon above. But now I still have some extra electrons. So that's number 4. I'm going to put number 5, keep going clockwise over on the left. Now that each side has 1, they're spread out, nobody's crammed in there. Now I can start refilling those empty spots that I left open. I can put number 6 back on the right again, and continuing to move clockwise still, I put number 7 down on the bottom. I've now got 1, 2, 3, 4, 5, 6, 7 electrons. That's all I had to work with, so everybody's there. They're all in the right places, and I still do have one spot over here that's kind of empty, where if I had an 8th electron, it could have gone there, but I just don't have an 8th electron, so it's empty. We leave it alone, don't do anything with it. That's all I've got there. All right, now let's have you try some of these. You've got these 6 examples on your pages. Do the exact same thing we just did in the last slide, but now you get to look it up. So for magnesium, we have to know what the symbol is. Magnesium is Mg, so I'm going to just write an Mg right here in this space. And I'm going to fill in the rest as I go too. So selenium right underneath it is Se if you look that up. I'm just going to go before I do any of them and fill this in. Fluorine, our old friend, is going to be F. I'll write that down here. Oxygen is O. Chlorine is Cl. And gallium is Ga. Okay, that being done, now I can go back and do the rest of my steps. I need to look up how many valence electrons each thing has. Magnesium up top here, I can see a 2 at the end of the line here. So I need to write 2 valence electrons somewhere onto this picture. Our rules tell us that anything up to the first 2 can go on top. That's where you do it every time. So I'm just going to put 1 and 2 electrons on top, like little blue Mickey Mouse ears, and I'm done. That's the only 2 electrons I have to use. I have nothing else. I can't put them anywhere else. Magnesium's done right there. Selenium on the bottom here. I can see that there is a 6 last in line on selenium. So I need to put 6 electrons around the S and the E. Again, the first 2 go on top. So I'm going to put electron number 1 right here, electron number 2 right there. I still have a couple left that I have to go. So I'm going to move clockwise. Number 3 is going to go on the right side. Number 4, I don't put right underneath it. Number 4 goes on the bottom because I'm moving clockwise around, putting a single one on each side until they're all filled up, one each, and then I can go back and double up. So that's electron 1, 2, 3, and 4. I'm going to continue around clockwise and put number 5 over on the left side. And now that each side has a single except for the top, I go back and double up. So now I'm going to go back to the right clockwise and put electron number 6 over on the right side right there. It's kind of a weird shaped dot. Flesh it out a little bit. Actually, I'm going to redraw it because it's strange. Number 6 right there, and we're done. 1, 2, 3, 4, 5, 6 electrons. I do so, like on the previous slide, have these kind of blank spots right here and right here. If there were more electrons on selenium, that's where they'd go. There's not any more electrons, so we just leave it blank, and that's fine. Fluorine underneath. If you look up fluorine on your periodic table, it's element number 9, and I see that it has 7 electrons, so I would put, again, the first 2 up top, 1, 2, and then number 3 goes on the right. Clockwise, number 4 goes on bottom. Clockwise, number 5 goes on the left. Skip over the top because it's full already. It has its 2. We can't put any more there. So number 6 goes back on the right. Number 7 goes underneath on the bottom. Just like bromine on the last slide, I have that one empty spot where if there was an 8th electron, it could go there. There's not. And the same is going to hold true for chlorine over here, which is element number 17. It's right below fluorine, right above bromine on your periodic table. So it also has 7 electrons, so it'll look the exact same way. 1 and 2 on top, 3 on the right, 4 on the bottom, 5 on the left, 6 back on the right, 7 to fill in on the bottom, 1 empty spot. Oxygen up top, it's element number 8. It has 6 valence electrons. So as always, I'm going to put 1 and 2 on top. Number 3 goes on the right. Number 4 goes on the bottom. Number 5 goes on the left. Number 6 I fill in back on the right. It's going to look a lot like selenium, which makes sense because it's 2 spots above selenium on the periodic table. It's in the same column, same group, same family, so it'll look very, very similar and have the same kind of chemical properties. Last one is gallium. Gallium, if we look at our periodic table, it's element number 31. It tells us that we have 3 valence electrons. So I'm going to put numbers 1 and 2 on the top as always. And the third one goes right here. There's my 3rd electron. That's all I have to put down. I'm done with these. Try the rest of them on the next page. Do the same thing we just did here. You don't need to rewrite the chemical symbol. You can just draw the electron dots right onto these symbols that are already written on the page. I'm going to rewrite it just because I think the letters are a little bit small on this slide, so I want you to be able to see a little bit better, but you don't need to because you have it on paper. So for the first one here, it says Na, and we can use our periodic table to see exactly how many valence electrons sodium has. So I would just write Na here so you can see a little bit better. And when I go to my periodic table and look up how many valence electrons sodium has, I see a 1 in that last spot on its electron configuration. That means it only has 1 electron in its outer ring. And from the rules we've been using, the steps, I know that any of the first 2 electrons, if I have 2 electrons or more, I'm going to write them up top. I'm going to draw them up top. So because I only have 1, that's all I have to actually put on. So I'm just going to put that guy right here above Na. If I had a second valence electron, I would put it right next to it also on top. And then after that, I build around. But because I only actually have 1 electron, there's only one place to put it. I'll put it right on top of the Na. That's all we have to do. We're done with this. Do that same kind of process for the rest of these, and I'll see you on the next slide. If you've already finished drawing the electrons on those diagrams in the previous slide, your notes, you're good. If not, go back right now and draw the electron dots around all those symbols. We'll continue with this tomorrow and see how we can draw dot diagrams for ions in addition to the neutral ions we just saw now. And be ready in case I decide to have you draw a few of these on a quiz.